Now that Daniela helped us figure out the exact value of velocity necessary to keep the star in place during the orbit, we can start thinking about a very realistic scenario. Now, usually when astronomers hunt for extrasolar planets, they never actually see the planet itself. This is because, compared to the star it's around, the planet is so much tinier in both mass and physical size, and the planet's often a lot dimmer. In fact, it's always a lot dimmer than the star itself. So we're going to have our code simulate this in the easiest way possible by just getting rid of the visual of the planet and only seeing the star. So just as a reminder, if we take a look at the code as it is written now, we have this orbiting the sun as expected. We want the same picture now, but without the planet. And to do that, we'll do something very simple and just comment out. So draw blob is the function that we use to draw the planet. So by adding 2 slashes in front of this and playing, now we have the same picture as before minus the planet. The sun's motion is unaltered by this, and all the physics is still there, but now we just don't actually see where the planet is at any given point. And for the sake of cleaning up the code a bit, I deleted everything we input in steps 5 to actually show the average velocity of the star. So now, if we only see the star, and that's the only motion that we are familiar with, and we want to infer the mass of the planet, because that's usually the goal that astronomers have in mind, we have to be a little bit more creative. Now in this code, you can scroll up to the beginning and you see that mass is equal to 0.2, so 1/5 of a solar mass. But in real life, astronomers don't know this. If we did, we wouldn't have this problem. So instead, let's look at the motion of this star and do some physics and figure out what that mass is. So we'll begin by trying to measure the velocity along the y direction. And here what I'm calling the y direction is whatever the telescope is pointed at. So for example, if the object I'm looking for is over here, and then I situate my telescope such that it focuses right down that line, and I look through it, everything on that line is what I'm calling y. And then x, is some other direction that we don't really have access to seeing. I can't tell when something's moving if it's not moving along that line. It has to move along the line either to me or away from me. And that motion is going to be defined as the velocity along y. And we can use our code to help us figure out what that is. So I'm going to go here to step 8, where we measure the velocity of the star. We're going to copy in the clipboard, and under display and under draw, I want to put that line. A good spot to put it is right under where we had draw blob commented out. It can be anywhere as long as it's underneath display. And if I play that, what we see now is a graph of the maximum value and the minimum value of the y velocity of the star. So this is an important graph to have. Like I said before, ultimately we want to use this information to calculate the mass of the planet, which we don't have access to. But just as it is in this step, you can already see the length of approximately what you would call a year of this star. So for the star to make a complete orbit, in other words, looking at the graph going from a negative value to a positive value back to the negative value. So this is an important graph to have for a variety of reasons. One of those is that we're ultimately going to use information from this graph to calculate the mass of the planet, which is what astronomers are often after when dealing with extrasolar planets. The other thing we want to figure out is the length of a year on this sun. So what's going on? Right now, the telescope in our case is situated somewhere about right here, looking directly upward at the star. So it can see the star's motion not so much as it moves left and right, but as it moves up and down. And that's what's being plotted here in the graph. Notice the red arrow here in the star. As the red arrow points down, the red line over here is negative. It's below this solid black horizontal line. And then as this red arrow points upward, it's in the positive region of this graph. And when the arrow is pointing perfectly left or perfectly right, we're at 0. So this plot gives us a variety of useful information. One of those is the maximum velocity of our star. The other is its minimum velocity. And a little bit more subtle, kind of hidden in the figure, is its period. So what the period is more or less the length of what we think of on Earth as a year. The amount of time it takes, the Earth to orbit the sun, or any planet to orbit any arbitrary star. However, the time it takes for the planet to orbit the star is the same as the time it takes the star to orbit the planet. And this period is something that's going to be very valuable for us, and we need to find out what it is to go forward. So let's go about doing that right now.
Now that we have our velocity graph up, we can also find the period of this planet going around the sun. So remember, the period is a complete orbit of the planet going around the sun. So if we go to our code, go all the way to the bottom to where it says measure the period of motion, we're going to put in these two pieces of code that will help us figure that out. So copy the first part near the beginning just to set the variables or declare the variables. So since right here I have a change in time dt, I'm just going to add this to under that just so all the times are in that section. And then I'm going to go back to the code and copy this other whole section of code to the draw function. So again, this part of the code will just allow us to figure out the period of the planet going around the sun. Okay, so I'm going to put this piece of code under display and just paste it right in here. So remember how we said we like to tab everything just to keep things nice so you can read it clearly. These are a bunch of lines, so I'm not going to tab every single line, but just know that the code will work just fine if you don't end up tabbing these lines in. So now, when I push play, we will be able to see the half cycle time of this planet going around the sun. So now that you can see this better, we can compare this half cycle time to the period of the planet going around the sun, because half the cycle time, just like it has it in the name, it's half of the time it takes the planet to go around the sun. So that would be half a cycle. So the period is twice the half cycle. So the half cycle time, it says here that it is about 9. Therefore, if we multiply that by 2, we know that the full period of the planet going around the sun will be 18.